Welcome everyone, and thank you for joining today's webinar on product reliability testing. Our presenter today is Marcel van Doesburg, Operational Manager of Reliability Testing at Eurofins EAG Laboratories in Eindhoven. Our moderator is Ben Brewers, European Sales Manager, and I'm Melissa Campbell, Marketing Manager for Eurofins EAG, assisting with today's event. Before we get started, just a couple housekeeping items. All attendees are muted. However, if you have questions during the presentation, please enter them in the questions section located in your control panel or app. You may send questions at any time during the presentation. At the end of the webinar, a survey will pop up on your screen and your feedback is greatly appreciated. Now I will turn it over to Marcel.
Thank you, Melissa, for the introduction to this webinar. My name is Marcel van Doesburg. I'm operational manager of the Reliability Test Center within Eurofins Material Science. I have 10 years of experience in wet chemical analysis and 15 years of experience in reliability testing. And I'm also a board member of a Dutch reliability foundation consisting of approximately 50 companies. In this webinar, I will give an introduction about developing reliability test plans and how Eurofins Material Science Netherlands is able to help you with the reliability development process. But first, back to the content of the webinar. The webinar consists of two parts. In the first block, we will take a closer look at the background of reliability testing. And then in the second block, the designing of reliability test plans will be discussed in more detail. It will be examined how together with the customer, the lifetime of a product can be determined. And during the last part of the webinar, we will try to answer your questions. In addition to the lifetime test plans, Eurofins Material Science can also help you with the execution of these test plans and the needed material characterization. Two webinars on these two topics are now available on the Eurofins website, and you may listen to these webinars via these two links. Melissa will share the links with you in the chat. Let's start this webinar with the voice of the customer. What is the reliability of a product and how experience customers this? As technicians, we have very precise descriptions about reliability, what it is and how we can calculate it. But for consumers or so-called customers, it's completely different. Here are some statements from end users, and these statements tell you something about how customers experience a product. It is often related to the consequences. Let's say what happens if a product fails. It could be annoying or life-threatening, but the level of reliability expected by customers depends on the type of product. People expect higher reliability from medical equipment than, for example, a washing machine. So reliability is not only a statistical value, but also something customers experience during use. It's all about trust. Before we go any further, it's important to discuss two parameters. These are the reliability level and confidence level. First, reliability. Reliability is proven not in the moment of purchase, but in the test of time. When a product consistently performs day after day, it earns trust. This is a statement that indicates that the reliability of a product must be determined over time. Then confidence. Statistical confidence is not about certainty, but the degree of belief that the true value lies within a range we can measure. This indicates how confident we are about the calculated product reliability. Now keep those two statements in mind, and we will need them later on when we discuss those topics in the second part of the webinar. Now we know why reliability is so important for the end user. We are aware what the voice of the customer means, but why is it so important to do reliability engineering for a producer or developer? Why is it so important knowing and understanding the reliability of your product? There are several reasons. For example, are there safety risks? Are there standards we have to meet if you want to introduce a product to the market to ensure a specific reliability? What are the risks of introducing new technologies? What may happen if there are failures? Are there only issues with the hardware that prevent a product from functioning? Or maybe there are health concerns? Or are there other factors at play? Look at things like security or competition. These factors ultimately determine how much time and budget is put into reliability engineering. Reliability engineering becomes more important when the risks are greater. When we talk about reliability, we often link this to lifetime. A product does what it is supposed to do during a certain period of time, a certain distance, or maybe a certain defined number of cycles. And during this lifetime, products may break down. And we recognize three different phases. And the so-called bed tube curve describes the various types of failure that may occur during the life cycle of a product. The first period of the life cycle consists of infant mortality. And infant mortality is recognizable because of a decreasing failure rate over time. Failures that occur prematurely. Such failures occur because of manufacturing defects or damage during transit. That is also the reason for the decreasing failure rate. After the first phase, all of the products with a manufacturing defect are out of the population. The second period consists of random failures. For example, a flat tire. That's typically a random failure. Random failures are recognizable because of a constant failure rate. Failures which are not specifically time dependent and may occur at any moment. The last phase consists of wear out and fatigue. For example, the aging of a motor or battery. Wear out, fatigue, that's typically recognizable because of the increasing failure rate. Wear out mechanisms begin to dominate the end of life of a product. For designing a reliable product, time and money are needed. Reliability management requires a good balance between cost and reliability. And let's take a deeper look. On the x-axis, we plot the costs, and on the X the reliability of a product. The blue line shows the failure costs, and this means that if the reliability level of a product is low, it will result in a high level of failures and field returns. The cost for repairing, maintenance, or warranty claims will be high. Now look at the orange line. The orange line shows reliability program costs. Increasing reliability activities within an organization will reduce the failure costs. A combination of the two graphs will result in the green line and gives inside information about the optimum based on costs. Investing in reliability programs can mitigate the high costs associated with product failures, and overall is leading to savings and improved customer relations. A thorough analysis of both costs can help organizations make informed decisions. Reliability program costs are normally a combination of designing test plans, test execution, and data analysis. And all those steps ask for know-how and dedicated equipment. Buying your own reliability test facilities could be very expensive. And within Eurofins Material Science, we offer a lot of different techniques and knowledge to facilitate your reliability test program. In addition to cost management, there are also different classifications for reliability requirements. The basic level is characterized by the minimum legal requirements in the areas of safety, health, and environment. Think of CE mark or guidelines for general product safety. Or compliance with this legislation is mandatory to be able to sell a product on the market. Without compliance, a product may not be sold. The second or middle level concerns testing according to standards. These standards ensure quality assurance and can also help to comply with certain legislation. However, it's not mandatory to comply with these specific standards. Nevertheless, testing according to standards has major advantages. The method of testing is clear to the outside world, and you know exactly how the test is executed. Then the last step in the chain, the top level, it's not only about meeting legal requirements and standards, but also about continuous improvement of safety and reliability based on risk assessment and customer satisfaction. This can be used to detect risks and improve quality. For example, the use of recycled materials has a positive effect on the CO2 footprint, but what does it mean to the reliability of your product? Continuous improvement and investigation of the reliability of your product is necessary to meet the required reliability. So far, the first part of this webinar. Now we are going to take the step towards a reliability test plan. With a test plan based on the specific product information, we will come up with accelerated lifetime tests, with which we can demonstrate the reliability of a product. And we do that with a certain level of confidence. Let's take a closer look at how we come up with this test plan together with our customers. During the process of describing the test plan, a lot of points need to be discussed with the customer. And hereby a short overview about the items we are going to discuss. The first step describes the user scenario. What is the object we want to test and how will it be used under normal conditions? The user scenario leads to the discussion about lifetime and what is exactly end of life. I mentioned already a statement about reliability and confidence, but here it's also important to discuss what the reliability and confidence level should be. If this part is clear, we will investigate the relevant failure mechanisms and transfer it, defining the right stresses. Based on the expected real lifetime, we can calculate the test durations. At last, we should end with a verification protocol, how we are going to verify the lifetime and what are the pass-fail criteria. Let's start with the first step, the user scenario. In order to make a reliability test plan, it's important to first discuss with the customer what kind of product it concerns. What is the application and where will it be used? This includes the geographical location worldwide, but also whether it's an indoor or outdoor application. What are the environmental conditions to which the product is exposed during its lifetime? You can imagine that there are very big differences. Think, for example, of a light application that is hung in a stable on a farm. It can be exposed to large variations in temperature, but also large changes in humidity. And in addition, the application is also exposed to, for example, ammonia gas from animals. For example, if we compare this with an AED cabinet in which an AED kit is stored, then we see that other factors may play a role here. Consider, for example, the salt concentrations when such a cabinet is hung on the beach, but also the impact of rain and sun. In addition to the environmental conditions, the user conditions must also be considered. To use the same examples, an AED kit that hangs in an AED cabinet is used very little. And this is in contrast to light applications in a stable that may burn 24 hours a day. The user profiles are completely different for both applications. In addition, it can be checked how often products are cleaned and with what kind of cleaning agents. Behavior that may not be desirable but can be prevented must also be included. Think, for example, of a smartphone falling on the ground or vandalism on an AED cabinet. Once this information has been collected, we can create a good user scenario, the starting point for our reliability test plan. However, not all relevant information is known yet. One of the most obvious questions to discuss with a customer is what the desired lifetime should be. In the test plan, we must include what the lifetime of the product should be so that we can adjust test durations accordingly. This question can often be answered. Statements like it should last longer than the warranty period, or similar products have a lifespan of so many years. So far, no problem. The questions that follows is more difficult to answer. What is exactly end of life? An answer like the product should keep working is normally not enough. Clear pass-fail criteria must be drawn up to determine the end of life. As an example, let's go back to the AED cabinet that we discussed earlier. We understand that the cabinet must be able to open and close during lifetime, but to what extent is it decisive if the material discolors and the cabinet is no longer recognizable as an AED cabinet, or if there are small cracks in the housing? There are many things that can affect the end of life statement. At the beginning of this webinar, I talked about confidence level. And we also have to answer this question in consultation. A high confidence level, for example, 90 or 95% is of course nice if you look at the outcome. But it also means that you have to test a relative large number of samples. Depending on the test, this can be time consuming. An additional aspect is that the number of samples must also be available. The choice of confidence level is therefore based on several things. In addition to the desired lifetime that we want to verify with the reliability test plan, we also need to link reliability to the number of products that may have failed in percentage terms after the desired lifespan, the so-called reliability level. First, we're going to talk about the meaning of reliability. We already discussed this from our customer's point of view. But now from a mathematical point of view. Reliability says something about the probability that a system or component will do what it is supposed to do under certain conditions after a certain time. The longer a system or component is in use, the less reliable it will be. A car will have higher reliability after a few weeks of use than if it has been in use for 8 years. So there's a difference. Aging increases the chance that something will break in the car. We express reliability in the described equation, where failure rate and time play a role in reliability. As we can see in the picture, the chances of the system breaking down will increase as usage increases. Now, confidence. Ultimately, a test plan will result in a statement regarding lifetime. And this statement is always made with a certain certainty. If we test one product, the uncertainty about this will be greater than if, for example, 100 products are tested. As more products are tested, the bandwidth in which the actual one is located will become smaller and smaller. The confidence will be at a high level when more products are tested. We have now discussed the most basic input, but a lot of other information can also be valuable. If the product is already on the market, field data may be available. If field data is available, it may give a lot of information about the robustness of the product and any weak links in the design. The tricky thing about field data is that it is sometimes difficult to collect. This data has to go a long way from the end user to the retailer and ultimately to the manufacturer and finally to the reliability engineer. So there's a high risk of data loss. Communication and sharing information is always difficult. The second part, performing an FMEA, a failure mode and effect analysis. It can be another way to gain this insight. We also facilitate FMEAs from the Reliability Test Center, and together with the customer, we rank the various components and look at the possible failure mechanism. It is also possible to run pre-experimental tests to detect a failure mode. Think of HALT. HALT stands for Highly Accelerated Lifetime Testing, but contrary to what the name suggests, it says nothing about the lifetime of a product, but provides information about the weak links in the design. The weaknesses are exposed with a combination of tests. And we can also perform these tests within the Eurofins Reliability Center. Then finally, failure mechanisms that are generated during a HALT test, for example, they can be examined in more detail with the material characterizations lab. And at the material level, for example, the formation of cracks, change in bulk composition or degradation of a surface can be examined. This total approach allows a good picture to be informed of the relevant failure mechanisms that must be included in the reliability test plan. We have now found the right information to define the fail modes and translate them into the right types of tests. And let's start with the failure mode. This describes how we as users perceive the failure of a product. And for example, let's take a Bluetooth speaker. Suppose we turn on this Bluetooth speaker and then after pairing with a smartphone, it turns out that there is no sound coming from the speaker. This is how the user experiences it. Because we have researched the failure mechanisms using material analysis techniques within the Eurofins lab, we have been able to find out that the failure behavior is caused by a broken solder joint. A broken solder joint due to solder fatigue. Now that we know this, we can look at the different stressors that causes this failure behavior. And this failure mechanism that is caused by mechanical impact. This can be vibration or falling of the Bluetooth speaker. And when it comes to falling, we can translate this into free fall testing, where we are going to perform drop tests at different test heights in different directions. We have now made the translation from the failure mode to determine a specific reliability test, in this case, drop testing. And if we know the right type of testing for a specific failure mechanism, we can also calculate the acceleration factor. And therefore, we take the following example to explain this. What we see over here is a building with different heights. On the various roofs, there are planters made of polymers. And what we want to do, we want to investigate how this material behaves if the planters blow off the roof and fall to the ground. The stress factor is therefore a mechanical load, the falling of the planter onto a concrete surface. Let's make the assumption that when designing the planters are made in such a way that they have to survive 50 falls of the used stress level. And if we wanted to test this, a fall could be simulated 50 times in combination with this fall height. To speed this up, introducing an acceleration factor, we are going to stand on a high roof, the medium or high stress level. And for the model, it's important to know how many falls the planter survive at each level. Will the number of falls that the planter can survive half if the fall height doubles, or is there another function? The correlation between U stress level and a higher stress level is important over here. And no, this is not an example of the everyday test request. Planters falling off buildings is not the most realistic scenario, but it does provide insight into the approach. We can apply this approach to a very wide variety of products, ranging from medical, consumer electronics, automotive, or recycle industry. The applications are wide-ranging. The next step is to make a translation between these real conditions and tests that we can perform into the reliability lab. It's important to be able to calculate an acceleration factor to shorten the test time, as discussed, but it is also important to make this translation in the right way. An acceleration factor that is too high can lead to the introduction of failure mechanisms that are not relevant but are caused by too high stress levels when performing the endurance test. And I want to show you two failure mechanisms which are not realistic. We stressed a Bluetooth speaker by means of a drop test, and if the drop test is too high, the enclosure will break after one drop. And the second one is the temperature test. If we stress the Bluetooth speaker at a temperature which is too high, we introduce a deformation of the enclosure, which is also not a realistic failure mechanism. And another example is the user profile for a smartphone is set at 20 degrees Celsius and 50% relative humidity. Then an acceleration factor can be applied, for example, testing at 70 degrees Celsius with a relative humidity of 95%. And of course, the question could be asked, why not to test at an even higher temperature to introduce a higher acceleration factor and resulting in a shorter test time. So there's always the discussion, how far can we go with the acceleration factor? Another stress factor can be the transport of products. The smartphone that we just buy new in the store already has a transport route on it. Think of vibrations in a truck or airplane, or maybe the box which the smartphones were transported in has fallen. And we can simulate this with a shaker or a drop test. The same vibrations are simulated, possibly at specific natural frequencies of the product. And also here, it allows us to introduce an acceleration factor. An acceleration factor can also be determined for chemical compatibility of materials if the contact time between detergent and material can be examined. Suppose a smartphone is cleaned with a detergent once a day for 4 years, then the contact time can be calculated and translated into a test duration. For solar and UV, it's important to look at the sun load of a geographical location and translate it back into a test duration. It can also be important whether products get wet during use. So there are different parameters we need to discuss before starting the tests. And then the last step we want to consider, that is the verification protocol. It is necessary that we can take measurements during the lifetime tests or at certain times to determine the status of the product. Does the product still meet the criteria? If in situ measurements can be carried out, it can be determined exactly what the degradation of the product is over time. Often it's not possible to measure this continuously, and that will result in sensor data where we only know that a product has failed in a certain time interval. Typically, measurements that can be done are current measurements, voltage, tensile strength for material characterization, sound measurements, but also, for example, a color point measurement. Depends on the type of test, type of product, types of materials. During this webinar, we mainly focused on drawing up the reliability test plan and how we go through this process together with our customer. In addition to drawing up these test plans, as a lab, we can also help you carry out the described accelerated live tests. This can vary from environmental testing, mechanical testing, or testing on chemical compatibility. After implementation, we can also help determine the lifespan and as described in the test plan and combine it with a statistical substantiation. In this way, we can give our customers insight into the robustness of the product, but also make a reliable, let's say, lifespan prediction based on the user scenario. In addition to guiding our customers with the preparation of reliability test plans and how this can be converted into a lifetime prediction, we also carry out many reliability tests ourselves. This includes climate tests, mechanical tests, and chemical tests. And I would also like to mention our halt equipment with which weak links in a design can be detected in a thorough way. All these techniques aim to provide insight into the reliability of your product. In this last technical slide of this webinar, I want to present 4 of our material analysis clusters. In this cluster, over 35 analysis techniques are there to help our customers answering their questions or solving their problems. In the compositional analysis cluster, we have experts working on the analysis of the chemical composition of gases, liquids, and solids. In advanced microscopy, we can make the beautiful images with a magnification over 1 million times. These images also can contain geometrical and chemical information of the sample. And when you want to know everything of the top few microns of your samples, the surface and thin film cluster is there to help you. You can think of surface optical properties, coating thickness, surface composition or contamination. The fourth cluster is physical testing. And physical testing includes the measurement of all kinds of mechanical and physical material properties. This also includes pore size and specific surface area measurements. And also here, the collaboration with the reliability test lab ensures that we can not only figure out a failure mechanism, but also mimic the fail conditions and even accelerate it. So why choose Eurofins EAG? There are many reasons why customers choose to work with Eurofins EAG. Since we are a global leader for material testing services, have ISO 9001 and ISO 7025 accreditations, we are the ideal partner to help solving your materials and engineering related product problems. And this brings us to the end of this presentation, where Ben Broers will join as a moderator, and let's discuss some of the questions.
Thank you, Marcel. Very interesting talk. Nice topic. And yes, I do have a question for you. The question is, what are the challenges when one designs an accelerated aging test?
That's a good question, Ben. Yeah, one of the most challenging things is replicating the real world conditions. It's difficult to perfectly replicate environmental conditions that occur over many years, and also finding the right acceleration vectors. If, like already mentioned, if the acceleration factor is too high, then you introduce failure mechanisms which are not relevant, and if it's the acceleration factor is too low, it will take too many time. And of course, also the interpretation of the data after test execution and finding the specific material, specific challenges. So it could be, yeah, there's a wide range of questions which needs also to be answered after the test execution.
Okay, thank you. Another question I have is, can accelerated aging tests be used for all types of products?
It can be used for a lot of products, but sometimes, for example, organic products like food or pharmaceuticals, they may not react predictably to accelerated aging because their degradation is also influenced by biological factors. And sometimes highly specialized or one-of-a-kind products may not have enough comparable data to determine suitable, let's say, test conditions.
Okay. Then I have a question for you from the chat, and that is, I'm wondering where quality fits in. If we send out, for instance, 100 products and one of them fails after the test over a period of, let's say, 5 years, would it still be a reliability?
I missed the last part of your question, Ben.
Okay, then I will do it again. If we send out, let's say, 100 products and one of them fails after the test over, let's say, 5 years, would that still be a reliability issue? And how do we prevent that?
It depends on the discussion we have to discuss it with the customer. What should be the reliability level and the confidence level? It is possible that you design a test where it's allowed that you still have a few failures during the test. That's possible, but therefore you need a larger sample size. So it is possible, but it's all based on reliability and confidence level. It could be still a reliable product, but yeah, it depends on what the reliability level should be.
Yeah, I can imagine when we talk about planes, if we have 100 planes, one drops down, then you will say it's not that reliability. That's something I understand.
Yeah, yes, of course, but you may expect that if you talk about planes, that reliability level of a plane is very, very high.
Yeah, let's hope so, and we are sure about that.
Yeah.
Another question, Marcel, that I have is, how do you monitor and evaluate the results of accelerated aging tests?
That could be a combination of visual inspection, checking discoloration, cracks or physical changes, mechanical testing. It could be also chemical analysis, where we use techniques like spectroscopy, where we check differences in material composition, electrical tests, or also test after aging, post-test analysis, where we compare aged product with products which are not aged, and then we verify the differences.
Okay, and then in relation to this question in the chat, do you have any experience in performing reliability tests on photonic devices?
Specifically for photonic devices, yeah, we have some experience, but I think we should discuss it with this customer, that we can see what we can, how we can help them in a proper way.
Okay, I think that's useful, and I also think in this case, this person who requested it knows how to contact us. What is the best moment during the product creation process to prepare for a reliability test plan?
That's good. That's a good question. In most cases, in my opinion, customers come in when they have already a complete product and they want to verify the lifetime. But it should be better if we are already in contact with each other in the design and development phase, because that gives you already an early insight information about reliability requirements, and gives you also the possibility to design for testability. How you can, if you look at your design, then you can already think about how you should test it when it's completed. And that's easier if you discuss that in an early stage. Also, based for an FMEA, for example, it could be very valuable if to find early weaknesses, and that in that case you don't have a complete product already, but it could be helpful to discuss it and what's important if you talk about reliability. But also there you need some samples that you can discuss that with each other, between the reliability engineer and the customer.
Yeah, I'm quite sure that reliability testing is not done just on based on the screen and the CAD file, so to speak. You need more information to test it. And then it's quite clear that Eurofins EAG can help me with setting up a reliability test plan. But to be sure, you can also help us with executing the test and judge the results and the failures that are appearing.
Yeah, normally we recognize 3 different phases. The first one is designing the test plan, as discussed in the webinar. The second part is the test execution, and that could be solar, UV, climate testing, mechanical testing. And then the last step is also the data analysis, where we come to a specific lifetime prediction.
Okay, no, I think for me it's clear, Marcel. I hope it was clear for the audience as well. I don't see any questions anymore. So thank you for the presentation, Marcel, and I would like to hand over to Melissa for the final part of this presentation.
Thank you, Marcel and Ben, and thank you all for attending today's webinar. If we didn't get to your questions today, we will follow up with you soon, and we will also send you a recording of this webinar. You can view our other reliability webinars by using the QR codes on your screen or the links in the chat. And if you have any other questions, please send them to one of the email addresses on the screen. Once you leave today's webinar, a survey will pop up on your screen, and we would really appreciate your feedback. And so on behalf of Eurofins EAG Laboratories and our presenters, thank you for joining us and have a wonderful day.